In the last class, I have discussed about what is soil structure or soil foundation interaction, and then I have discussed about various mechanical model where the soil is idealized by spring for the, and then for 2 parameter model soil is idealized by spring and the shear layer or spring or by tension membrane or spring and then by beam. Because in the first soil model that I have discussed is Winkler model, where the soils are idealized by spring, and those springs are linear spring, discrete, and there is a lack of continuity in those springs. So, to remove those limitations, then the improved models are suggested, where those continuities are removed, where then the springs are connected by tension membrane or by a shear layer or by beam. So, the next model that among those improved model is the Carr model. In the Carr model, in the last class I have discussed about the Pasternak model, where suppose this is the surface and these are the shear layer, and these springs are connected by this shear layer. So, this is that shear layer and loads are applied on this layer. So, this is the model which is proposed by Pasternak. So, this is shear layer and this is spring, and the expression was the shear modulus of G shear layers is G p and the spring constant of the spring are K s. So, the expression that was available for this case, that Q x y is K s into W x y minus G p del square W x y. So, these are the model that I have explained in the last class about the Pasternak model. In the Carr model, that suppose if this is x, in this direction this is z. So, similarly, in the Carr model we will get, so this is x direction and perpendicular direction this is z, and this normal downward direction this is z, and in this direction this is y. Then first soil is idealized by these springs, and then this shear layer is placed in between two springs. Then springs are again placed to idealize the soil. So, that means here this is the shear layer with shear modulus G p. This is, and here again the load is applied with Q x y, or concentrated load can be also applied. Now, here we will get, so this is springs with spring constant, with spring constant say k, k 1 K2 and this is the spring constant K1. So, this is produced by the car. So, this is the car model. So, these are the two where both the cases shear layer is used, but in the first case Pasternak model shear layer is used top of these springs to connect these springs. Here the shear layers are used, shear layer is used in between two springs to connect these springs. So, with different spring constant. So, here it is K1, it is K2, K1 and K2 are the spring constant and G is the shear modulus of the shear layer. Now, in that case the response function will be for the car model 1 plus, if I consider this is K2 by K1 to P or Q is Q x y, that is equal to G by K1 del square Q x y plus K2 W x y minus G del square W x and y. So, here another term that here this is Q x y K is W G P del square W. Here these terms K1 and K2 that will be introduced here. So, now if that K1 is 3 times of K2, then this expression will be 4/3 Q x y. If I put K1 is 3 times of K2, then this will be 4/3 Q x y minus G K2 del square Q x y, that is equal to K2 W x y minus G del square W x y. So, we will get this type of expressions which is similar to the Pasternak model. So, but here the advantage of this model over this Pasternak model, that instead of 2 parameter model, here we can use the another parameter, or you can use the 2 different types of soil with modulus of separate reaction K1 and K2. So, and then this is the advantage of this model, so that we can use that additional boundary condition is also available for this model car model. So, that means here we will get 2 spring constant K1 K2. So, we will get another parameter. So, we can represent the soil behavior more correctly. So, now in this case, so this is the two other different model for where the soils are idealized by spring or shear layer, or to connect those springs you can use beam or tension membrane. Now, in the another limitation of the so that means in the last class I have mentioned that there is basic 2 limitations in the Winkler model. One is the lack of continuity. So, by this improved model we can remove that limitation, because here the continuity is provided by using different components. And then the next one is that in the Winkler soil model, we that is the linear spring is used, but if the soil behavior is non-linear, then how these linear things can be converted to non-linear things. So, that is another limitation that you have to remove there. So, now in the for that part, if I consider the non-linear behavior of the soil, then we will consider soil, or you can consider that the nonlinear model. Now, first model that will use that for the nonlinear part, that model, that the elastic plastic representation of the soil. So, that is elastic plastic So, the elastic plastic representation of a nonlinear response. So, suppose you have the pressure here, this is W, the settlement, and Q is the pressure. So, we have Q and the W, and the soil behavior is this one. This is the load settlement curve of the soil. So, now here we will get a elastic and elastoplastic response. Then if I draw a tangent here, initial part, and then another on the final part. So, that is the intersection point, and here we will get, say, the settlement is W 0. So, we will get now this nonlinear response of the soil, this is the actual response, is now converted to a linear thing for the elastic one, initial portion, then the plastic, that is the elastoplastic response. Okay. So, now we are converting this nonlinear response to a elastoplastic response. So, that means for the initial part, the Q relation will be K 1 into W. K 1 is the initial modulus of subgrade reaction, or the initial spin constant of this initial straight line. So, that means that will be valid for any W which is less than equal to W 0. So, if W is less than equal to W 0, then the response will be Q equal to K 1 into W. Now, the next one, this Q will be K 1 into W 0, that for W greater than equal to W 0. So, in the next part, that Q will be K 1 into W 0, and that W 0 is constant, because this is the second part, that will be Q equal to K 1 into W 0 if W is greater than equal to W 0. So, this is one model, nonlinear model. Next nonlinear model, the bilinear representation. In bilinear representation, suppose we have load settlement curve. So, this is W is the settlement, Q is the pressure, then we have two straight line. This is one linear portion and this is the another linear portion of the curve. So, actually this is the again the nonlinear behavior of the soil. So, this is the actual behavior of the soil is this one, red one, that is the nonlinear behavior of the soil. So, those things we are converted to a different form. First one is the elastoplastic representation, and second one is the bilinear representation. This is the initial part, and then the next another linear line. So, if I extend that second line, so that value, so that is the q 0, and then we will get deflection of the intersection point, say W 1. So, we will get stiffness, or the K 1 is the spring constant and K 2 is another modulus of subgrade reaction. So, now we will get the response Q equal to K 1 into W, that for W less than W 1. And next one, Q will be Q 2 into W plus W 0. So, here this value is, say, W 0. So, this is for W greater than equal to W 1. So, we will get this second response K 2 into W plus W 0, or we can put any other value. So, that is the 2 bilinear representation of a curve. In the third model, that model which is defined, that is a nonlinear model. That is one thing is proposed by Chandra. (1979), where this is soil behavior, this is settlement, and Q is the pressure. So, we will get a polynomial relationship, that we can use Q equal to K 1 W minus K 2 W to the power Q. Now, to determine K 1 and K 2, have to plot Q by W versus Q square. So, now if I put, that is Q by W, this will be K 1 minus K 2 W square. So, now if I plot this Q by W versus W square, then the slope of this line will give the K 1 value and the intersection intercept will give this K 1 and K 2 value. So, that means from here will this K 1 and K 2 value. So, suppose we will get this type of curve. So, if I plot W square here and Q by W, then we will get this type of curve. So, that slope and the intercept, that will give us. So, this will give us the K1. So, intercept will give us the K1 and slope will give us minus K2. So, the slope that will give us minus K2. So, that means slope and intercept from these two things will get the K1 and K2 value. So, this is another representation of the nonlinear response of the soil. And then here in the previous response, that here we have used this value is Q 0 because W 0, and then we use this expression, though that part will be. So, this is the two response, one is elastoplastic representation, one is bilinear representation, and then third one is the nonlinear representation. So, another nonlinear representation you can provide, that is provide Contd, (1963), where also suppose this is a nonlinear behavior of the soil, and initial part that slope is a Q 0, K 0. So, K 0 is the initial modular coefficient of modulus subgrade reaction. Or initial spring constant. And then, so suppose this is again Q is the pressure, W is the settlement, and if I draw this parallel line from this ultimate load point, then we will get this point is Q ultimate. So, this value will give Q ultimate. So, Q ultimate is the ultimate load carrying capacity of soil. Then according to Contd, the representation is Q K 0 or K S 0 W 1 plus K 0 W Q ultimate. So, this is 1. So, this is another nonlinear representation of the soil behavior. So, these are the few nonlinear models that we can use. So, in the Winkler spring also these springs are assumed as a linear model. So, using this nonlinear model we can remove that limitation also. So, the next thing, that is the another thing that will start, that is elastic continuum model. So, in the elastic continuum models, that is continuous response of the soil medium seems from the work of Bouchinic. So, that is first Bouchinic propose this work on this area. So, that year is 1985. So, according to the Boussinig, that we analyze the problem as a semi infinite. So, that is a semi infinite homogeneous isotropic linear elastic solid. So, here the soil is idealized as semi infinite homogeneous isotropic linear elastic solid, which is subjected to a concentrated force which act normal to the plane boundary. So, here it is subjected to a concentrated load which is act normal to the plane boundary. Now, first that we will consider that for the isotropic elastic continuum, so suppose we have one, this is soil surface and concentrated load is applied here. This is x direction, this is z direction. So, there will be one deformation will be in this form. So, that means here we will get this is u, this is w are the two different deformation component. So, in the plane strain problem or in the plane problem, a state of plane strain exists in the x z plane. So, plane problem, the state of plane strain exists, the plane strain exists in the x and z plane. So, displacement component v in the y direction is 0. So, displacement component v in y direction is 0. So, first we are going that elastic continuum models. The Boussinig first proposed that. So, here the first model that we are taking the isotropic elastic continuum, where in the plane strain problem that will exist. Suppose we apply a load P, the plane strain problem exists in x z plane and displacement component V in y direction is 0. So, the non-zero stresses, that is sigma x x, sigma y y, sigma z z and tau x y. So, these are the non-zero stresses. So, that the surface deflection W at x 0. So, W x at 0 point in the z direction can be. So, the surface deformation surface displacement in z direction Wx, that will give 2 p1 minus mu s square divided by pi es into log x plus c. So, the surface displacement in z direction in this plane problem, that will be 2 p 1 minus mu s square pi es log x plus c, where c is an arbitrary constant. So, c is an constant. So, c is an arbitrary constant. So, now we will get this expression if it is a plane problem which is a concentrated load applied on the surface. In the next problem, that if the UDL is applied on the surface, suppose the same thing, this is x direction here, this is z direction. So, one uniformly distributed load which is applied, whose intensity is q, and width of this loaded region say 2 b. So, in that case we will get another expression of the displacement of the surface of the half plane subjected to uniform distributed load u. In that case, W x z will give 2 q 1 minus mu s divided by pi g s 0 to the power infinity e to the power zeta z by zeta square 1 plus zeta z sin zeta b cos zeta x d zeta, where q is the stress intensity of the load and G s is E s divided by 2 1 plus mu s, that is shear modulus, and E s is elastic modulus or Young modulus, mu s is the Poisson ratio. So, this is the expression for the if it is uniformly loaded region. So, the next one is isotropic elastic Haaspel. So, that is if I go for the isotropic then the displacement, if we consider that in the surface of this loaded region. So, that means, if the surface applied a concentrated load, this is in the direction of r, this is in the z, and another one applied the UDL with 2 a the loaded region, this is z, this one is R. So, we will get a axisymmetric condition. So, that means here for the isotropic elastic half space, then we will get the surface deflection for the concentrated load P dash, and here the intensity in Q dash. So, we will get W R into Z R Z is equal to P dash 4 pi G S R to 1 minus mu S plus Z square by R square. So, here similarly G S is the shear modulus, and mu S is the Poisson ratio. And we will get R square is equal to small r square into Z square, that is capital R square is small r square plus Z square. So, if is the uniform loaded is applied, then the deformation will be R Z Q star into A divided by 2 G S 0 to infinity 1 by eta to 2 1 minus mu S plus turn to Z e to the power minus to Z into Z 0 eta R to Z 1 eta A into D theta. So, and the surface deflection at the center of the loaded region. So, this is at the any point. So, at the center displacement at the center of the loaded region will get W 0 0, that will be 1 minus mu S Q dash A divided by G S. So, now here this Z 0 term and Z 1 term are 0th and first order Bessel function of first kind respectively. So, these are the two different condition. One is concentrated load, another is UDL for isotropic elastic half space medium. So, the next one that we will consider, that is the third type of condition that we will consider, that is the orthographic elastic continuum. So, that is your orthographic So, that is orthotropic elastic continuum, where we will get the expression that is available that q x z that is equal to q, if it is a UDL, pi k1 minus k2 integration L12 by k2 minus L22 k2 T2 L12 k1 L22 k1 T1 to dz. So, there we will get the deformation for this condition. So, here L12 is mu dash 1 plus mu divided by E z, L22 is equal to 1 by E z 1 minus mu dash square E x by E z, L11 is equal to 1 minus mu square by E x, and L44 is equal to 1 by z dash. Now, k1 dash k1 square is equal to 1 by L22 into L12 plus L44 by 2 plus c to the power half by 2, and k2 square that is equal to 1 by L22 L12 plus L44 divided by 2 minus c to the power half by 2, where c is equal to 4 L12 square plus L44 square plus 4 L12 L44 minus 4 L11 L22. So, these are the expression by which we can determine for the orthotropic elastic continuum case what will be the deformation, surface deformation, and then here we will get that E is the, here we will get the E, and somewhere we are using that E dash. So, we will get the E will be the Young's modulus for the plane of isotropy. So, E will be the Young's modulus for the plane of isotropy, and E dash will be the again Young's modulus for directions perpendicular to the plane of isotropy. Similarly, we will get the expression of G, that G is, if I consider that is E divided by 2 1 plus mu, that is shear modulus for the plane of isotropy. Similarly, G dash will be shear modulus which which characterizes the distortion of the angle between isotropy plane and its normal. So, we will get, if we get E dash is the Young modulus in the plane of isotropic, E dash is the Young modulus in the direction of perpendicular to the plane of isotropic. Shear modulus is the shear, G is the shear modulus in the plane of isotropic, and G dash is the shear modulus which characterizes the distortion of angle between the isotropic and its isotropy plane and its normal. Similarly, we have mu and mu dash. So, similarly, the value of mu is Poisson ratio which characterizes the contraction in the plane of isotropy. So, basically here xy plane when tension is applied in the same plane, and mu dash will be the Poisson ratio which characterizes the contraction in the plane of isotropy when tension is applied in the direction perpendicular to this plane. So, we have two mu, one is mu and mu dash. So, mu dash is the Poisson ratio which characterizes the contraction in the plane of isotropy when tension is applied on the same plane. Another is Poisson ratio which characterizes the contraction of the plane of isotropy when tension is applied direction to the normal of this plane. So, one the different direction of the tension, one is applied to the same plane, another to direction to the perpendicular to the plane, then this will give you the mu and mu dash. So, these are different model that we are talking about. So, next model that we will explain, that is the Vlasov model. So, in the Vlasov model, so that means in the consider the state of plane strain. So, this is considered state of plane strain in the elastic layer in the xz plane. Then the displacement components are So, u x z that is equal to 0, then w x z that will be w x into h z, where h x z or that is describe the variation of displacement w x z in the z direction. So, we will have the h x z function which will show the variation of the displacement y x z in the z direction. Now, several variation have been proposed, including the linear and exponential variation. So, several variation is proposed, including the linear and exponential variation. So, now if we have in the Vazov model, if we have the soil, let us suppose it is x, and here we have a z direction here. Then if this is the thickness of the soil layer is h, and we have one component segment if I consider, and if load is applied over there with the intensity q x, then this segment is dz, then definitely we have tau x z, because here the stator plane strain elastic layer in the x z, this is the x z plane where this is the elastic layer we consider, and displacement components u x z 0 and w x z is w x and h z, where h is a variation of the describes the variation of displacement in the z direction. Now, several variations of tau x, if we have the tau x here, then tau x z plus del tau x z divided by del x to dx. So, we have this variation. So, now this variation of different h v value. So, h z that will be 1 minus nu, where nu is equal to z by h. This is one variation, and another one we can say this is h z that is equal to sin h gamma h minus z divided by L divided by sin h gamma h divided by L. So, here gamma L are constant. So, now the expression using the principle of virtual work, the expression of the q x the final response function that we will get, that is k into w x minus 2 t d square w d x square, this is w x. For this model we will get, so here also this is a 2 parameter model where we will get k is one parameter, t is another parameter. So, where k is related to E 0 1 minus mu s 0 to h d h d z to the power square d z, and t is equal to E 0 4 1 plus mu 0 0 to h a square z dz, where E 0 is E s 1 minus mu s square and mu 0 is mu s 1 minus mu s. So, it is very important to note that G p t and k s are directly related to E s and mu s, where E s is the Young's modulus of the soil and mu s is the Poisson ratio. So, these are the response that we will get for this Blasov model. Now, so in this class we have discussed about various other type of model, improved model and then some nonlinear model to overcome the limitation of the Winkler model, and then how to determine the settlement response at various different conditions of the, that is also explained in this class. So, next class I will explain about the how the beams behaves if it is resting on elastic foundation. Thank you.